In our last video, we worked out all of these geometric properties of the gradient, these three here, and these two here. Let's use these properties to apply a bunch of different cases, both computationally and also pictorially. So to start off with, I just drew a contour map here for this function f of xy is equal to y squared minus x squared. So the blue lines here are the contours. This is at 0, this is at 0. And the idea here is that like up here is high, you know, like this is like 10 and 20. I didn't put numbers on it, but like 10 and 20, 10 and 20 down here is also high. These are low, these are valleys as you move off to this side. -10, -20, -10, -20. So the thing that I want to do is that I want us to draw on the gradients the direction of the gradient. We might not know how long the gradient is, but we can draw on at least the vector is pointing in the direction of the gradient at a bunch of random points here. So the ideas that are going to be most important here is that the gradient always needs to point in the direction of the maximum rate of increase. We want to be moving up the hill, and we want to be moving up the hill as quickly as possible. And alongside of that, the gradient needs to be orthogonal to the level curves, to the contours. It needs to be perpendicular to the contours. So, for example, at this point right here, I need to draw something that is orthogonal to the contour, and it needs to be moving up the hill in this direction. So, yeah, I'll just kind of say here, this is the value, this is the vector in the direction of the gradient. I might not have the length right, but at least I've got the direction right there. Again, right here, it needs to be orthogonal to the level curve, but going up the hill. At something like right here, orthogonal and going up the hill would be heading straight up in that direction. Over here, orthogonal going up the hill would be like in that direction. All of these, they need to be orthogonal to the level curves. How about somewhere over here? So like this is, as I said, like -20, -10. So going in this direction is going up the hill, because going that way is going down into the valley. So that's where the direction of the gradient is. Down here, going in this way is moving up the hill. So something like that seems to work. Something like that seems to work. And we can do as many of these as you want. So low going to the high. So something like that works here. Something like that works here. So we can do as many of these as you want. Amuse yourself, draw your own contour map or something like that, and just practice drawing gradients. Okay, that was the first example I want to do in this video. Second one is, this is going to be a hill here. So let me put contours 100, 200, 300, 400, and 500. And so the thing that I want to do now is, so once again, we're going to use the fact that the gradient points in the direction of the maximum rate of increase. And we'll again use the gradient is orthogonal to the contours. But now I want to use this fact a little bit more. The magnitude of the gradient yields the maximum slope of the tangent line to z. The maximum slope is the maximum rate of increase. So the bigger the maximum rate of increase, the bigger the magnitude, the length of our gradient is. And so let me show why I'm kind of making a big deal about this. So let me draw 2 points on here. One point is going to be right here. We'll call that point P. And so point P is gradient is pointing in that direction. It's going up the hill, and it's going to be orthogonal to the it's going to be orthogonal to the contours. And right here, let's call this point Q. So again, we know that the gradient for Q is going to be point up the hill, orthogonal to the contours. My question now is, what can we say about the relative lengths of P and Q, the gradients there? Well, if you're standing at P and you're kind of walking up in this direction, you're not increasing your height very quickly. This is a nice, gentle stroll up the side of the hill. But if you're going up this way, the contours are very, very closely spaced together, which means that you're very, very quickly increasing your height, which means that the gradient is very large in absolute value here. And so, we might not know exactly how long to draw it, but we really had better draw. So both of these, that's supposed to be orthogonal, and that's supposed to be orthogonal there. But here, we are going up the hill a lot more quickly at Q than we are at P. So how does that, so using this thing here, the bigger the maximum rate of increase, the faster we're going up the hill, the longer the gradient needs to be here compared to here. So I think this is a very instructive example. Again, kind of getting after, this difference. We can't draw exactly how long the gradient needs to be here. I mean, it might not be to scale or anything, but we sure can get the relative magnitudes of those two gradients. Okay, so that's a couple of picture examples. What can we do with drawing pictures? And the third example that I want to do here is a computational one. So let f of xy is equal to x to the fourth y to the negative 2, and P is the point 2, 1. So let's find a unit vector in the direction of the maximum rate of increase at P and determine that maximum rate. So I like giving you this question. You might want to pause the video and think about it for a little bit. But I like this question here because this is a question about gradients, but the word gradient doesn't appear in the question at all. Find a unit vector in the direction of the maximum rate of increase at P. Well, that's just asking you, by this bullet point here, to find a unit vector in the direction of the gradient. So let's go ahead and do that part of the problem. So the gradient of f is going to equal, partial derivative with respect to x is 4x cubed y to the negative 2. Partial derivative with respect to y is negative 2x to the fourth y to the minus third power. Okay, and at P is the point 2, 1. So this would be 4 times 2 cubed is 8 times 1 to the minus 2 is just 1. Negative 2 times 2 to the fourth will be negative 32 times 1 to the minus third is just 1. So this is, I'm sorry, I made a mistake here. I forgot to multiply that 8 by that 4. 4 times 2 cubed, 4 times 8 is 32. Okay, so this is the gradient here. So we need a unit vector in the direction of the gradient. The magnitude of the gradient here is going to be 32 times square root 2. Check that for yourself. So if we divide these entries by 32 square root 2, u ends up as 1 over square root 2, comma, negative 1 over square root 2. So that's the first part of this problem. Second part of this problem, determine the maximum rate. Well, that goes back to the magnitude of the gradient gives the max slope, gives the max rate of increase. So this is asking us for the magnitude of f of p. The magnitude of f of p, I mean, we just worked out there, is equal to 32 square root 2. Okay, so this was a bunch of examples, things that we can do with all of those geometric properties of the gradient.